Hello. Okay, so we will start at 6:05. Okay, if anyone joins. Okay, so I think we can start. Okay, so welcome to the third tutorial of the course Nuclear Astrophysics. Uh, so first, at first I will put the link of the previous videos in the chat box if any of you want to access them, you can access from that playlist. There are two previous videos there, and I will upload this tonight, so you can access that if you want. Okay, so now so we will start today's discussion, but before going directly to the content of third week, I mean mainly I will focus on the third week lecture in today's tutorial, but before that we will do a very quick revision of what we have done till now in the nuclear astrophysics course. I will not touch all the topics, but only the important topics in respect of astrophysics, okay, or the nuclear astrophysics. So in the first 2 week already we have done something, we have gathered some knowledge, so that I have written in point wise that what we have already learned. So the first important thing we learned is the HR diagram. So now all of you knows that HR diagram, there will be absolute magnitude in the y-axis and temperature in the x-axis, and that will look like this, the main sequence. And you know all the things about the main sequence, the supergiants which will be there, the white dwarfs, the here, all those things you have already done. So this is very important for the HR diagram, and you can also think of as a luminosity temperature diagram also. So luminosity the right side and absolute magnitude is at the left side. Okay, so this we have done in the HR diagram. Next to an important thing we do is the ML relation, that is the mass luminosity relation of stars, and I have told you that this mass luminosity relation is actually a empirical type formula. It is not so solid in theoretical, but it has been calculated using the observation, and roughly it follows m to the power 3.5 times spectrum. Okay, so all this thing we have done. Just a second, let me see my note. Yeah, then we did the Hubble's law, which tells you the relation between the distance and the Hubble constant. So that can be, and the velocity. Okay, so velocity can be written in terms of h0d, where h0 is the Hubble constant and d is the distance of that astrophysical object from the measurement point, you can say from the earth, and v is the velocity of that object. So this is a famous Hubble's law, v equals to h0d. So, and we have calculated, we have done mathematics using this particular law. So we have calculated the velocity of a particular object. And one important thing I should have put here, we have also done the redshift of electromagnetic wave. Okay, electromagnetic wave. So z is equals to delta lambda by lambda, where delta lambda is the change in the wavelength due to the velocity of that particular object, and this lambda absolute is the actual lambda, which actual wavelength which is emitted in the frame of that object. So that we already calculated, and this redshift is a very important thing in the astrophysical scenario, from where you can measure the distance, the velocity of the particular object. So both the Hubble's law and the redshift, comparing the both Hubble's law and redshift, you can calculate the unknown parameters of a particular stellar object. So this we have also done. Then the one of the main important things is the CMB, cosmic microwave background, that I have also told you that what a cosmic microwave background is, how it is coming from the epoch of the last scattering surface. You don't know need to know the actual terms, what is the last scattering surface, but you have to remember that this cosmic microwave background is the first light of the universe, you can say, and this also follows a black body like spectra if you measure the flux and at a wavelength, and the temperature is 2.7 Kelvin. Very important, you should remember this always, that this black body this cosmic microwave background shows a black body spectrum which have a temperature of 2.7 Kelvin and the peak is at a microwave range. That's why it is called the microwave background. I think 9 is okay. Okay, so this you have already seen, and this cosmic microwave background is a isotopic thing. It is so there is a problem with the light of my room. Okay, so I think it will be better to turn off the video. It may create problem. Let's see. Okay, so as I was telling, that's cosmic microwave background, and it is an indication of the Big Bang. This also we have read. Now coming to the nuclear astrophysics part, so we have done the thermonuclear reaction, that means which is the source. This thermonuclear reaction is actually the source of the flux of the stars. That means it is the fuel of a star. So the age of the star depends on the how much nuclear material it has inside its core, and the thermonuclear reaction release energy, which energy comes out of the surface, and we get that. I mean that energy is spreading throughout the universe. That is the reason. So the main reason of the flux is the thermonuclear reaction inside a star, and here I have written few process of different elemental making, that is from carbon fusion we get neon, from neon oxygen and higher order elements. So you know that oxygen burning process, neon burning process, silicon burning process, which give us higher and higher element in the universe. So this is the thermonuclear reaction which we have studied, and you have also studied an important thing, that is the Q value. So Q value is actually, if you, so this is the main thing which tells us how much energy will be liberated in a thermonuclear reaction. So this is actually M1 plus M2 minus M3 plus M4. So 1, 2, 3, 4 are 4 elements. 1 or 2 are taking part in fusion, and they are making 3 and 4. So this is the delta M, that is the mass difference between the products and the reactants, and then we multiply with the C square to get the energy. So delta M C square, which denotes the Q value, and which tells if Q value is positive, that means we gain energy from that reaction, and if Q value is negative, then we have to supply the energy for that reaction to occur. So generally fusion gives a positive Q value, that means energy will be liberated from the fusion, and that is the main energy source of a star. So all this we have, I mean this thermonuclear reaction and Q value are related, but I have put it in 5 and 6 number point because they are very important things. So all these things we have already done, and what I have not written is that we have also calculated the luminosity of a star, which can be calculated by 4 pi r square sigma t to the power 4, right, where T is the temperature of the object and r is the radius of the object. So luminosity we have calculated. From that luminosity we have also calculated the flux, which can be measured at a distance of d. So if this is the star which have a L luminosity, and you are measuring by sitting here, which is at a distance of d from that particular star, so this is actually d, then your flux will be the luminosity of the star by 4 pi d square. All this we have done, and we have also used magnitude nomenclature, which can be evaluated by using the flux, and that magnitude system, the apparent magnitude, the absolute magnitude, all this I have told you in the first and second classes. So these are the main thing which we have learned till the second week, and in third week we will mainly focus on this thermonuclear reaction in a deep we will gain some deeper knowledge in terms of nuclear the cross section of the nuclear reaction, the reaction rate, and all the other things. We will look into that in this third week. So we are going deeper now in the thermonuclear reaction, which is the main motive of this course. Okay, so I will focus on that part today, but in the last class some of our students, they told me that the assignments which I was doing is the older version, the newer version. So one student sent me the newer version. So he sent me all the assignments of the last 3 weeks, which you have already got. I don't have access to them. So I will go through some of the problems from those 3 assignments at first, which will be based on your first week, second week, and third week. And additionally, I will do some more problems from the older assignment of the third week, which will eventually help you to solve your future assignments. So at first I will do all those 3 previous assignments, and then I will come to the older assignments, which will require the knowledge of the third week entirely. Okay. Now one thing I have put here, this Hoyle prediction, because some of the student asked me that what is Hoyle prediction, she or he cannot understand it. So as far as I understand, that Hoyle prediction is nothing but, what I can say, it is prediction, because this 12C here, you can see this is the carbon which is which is taking part in fusion with another carbon, and it is creating the neon. Now how this carbon forms? So one of the understanding is that is called the triple alpha reaction. Triple alpha reaction. That means you have 3 He or the alpha, and they will create a 6C12. Okay, so this is called the triple alpha reaction. By that reaction, the carbon 12 forms, but the point is that the probability of this triple alpha reaction is very less. Now before Hoyle, there was some prediction. They have calculated the probability of occurring this particular reaction, and they have found out that the probability is so low that it cannot explain the observational abundance of carbon 12. I mean, this method of creating that C12 is very less. I mean, the probability of occurring is very less, so it cannot explain the abundance of C12. So the question is, from where that C12 is coming if this reaction probability is very low. So in that particular domain, Hoyle gives some prediction that he predicted that in 12C there must be a energy level which is 7.7 MeV. This particular thing I have directly taken a screenshot from sir's coaching. So sir's not coaching class. So if your carbon 12 has an energy level which is at 7.7 MeV, and some other constant is that should have the spin as 0 and plus parity. So if all these 3 condition holds, that means you have an energy level of 7.7 MeV plus your 0 spin plus your positive parity, then the probability of this reaction is high, this triple alpha reaction. Or here it has been written in the other way, that without an 7.7 MeV energy range, thus capture probability would be very small. That means Hoyle predicted that there should be this value of energy limit, which energy level which can explain the higher rate of this reaction, as well as the observational abundance of carbon 12, which cannot be explained if we don't consider this Hoyle prediction. So this was not known before, and Hoyle came with this explanation. So this is the main thing of Hoyle prediction, that which I told you. No other thing. It is, you can think of it as a theory, that Hoyle gives some theory of matching or balancing the reaction rate and the abundance of the carbon 12. Okay, so that is the Hoyle prediction. Now, okay, now we will go to the questions, and while doing all these questions, we will go through some other theory which we required to solve these questions. Okay, so these questions I have taken from your first or second assignment. I cannot remember it correctly, but some few individual problems I have taken. I have not taken all the problems because many of the problems have already done. So the new assignments and the older assignments are just I mean permutation and combination of problems. Some problem is there in the third assignment for the new version, it was in the first assignment of the older version. So more or less the problems are same or similar. Okay, so now let us start with some problems, that is, as it is a problem solving session. So here we have to calculate the resolving power of an optical telescope with a 24 semi aperture in blue light. Okay, so so there is a famous criteria which tells you that what can be the resolving power of a particular observational instrument, which can be telescope. So the main point is, when you are looking at something at a very far distance, I mean at a sky, then that can be viewed as this. So suppose you are viewing this at first, but with more or more resolving power, this source will look like this. So this will look like this, and that can be look like this with increasing resolving power. Okay, so resolving power is increasing along this direction. Just a notification. So that means at first that source which you are seeing as a single source, with the better resolution of the instrument, you can see that there are actually two different sources, but due to a poor resolution, at first you are not able to see it. So that indicates, I mean this is the main I mean essence of the resolving power. So with a better resolving power, so if you have more better resolving power, then you can see two separate sources which are looking like a single source in this first case. So that is called the resolving power, and there is some criteria called the Rayleigh criteria. Rayleigh's criteria. So if you go through any standard optics book and the diffraction chapter, mainly you will find it at the diffraction chapter. Okay, so then there you can find that Rayleigh criteria, which tells you what should be the resolving power of a particular system. So that I will just tell the criteria. That criteria tells that if you have two sources, that means they have two diffraction pattern, because when you are seeing, there is the I mean this, suppose this is a telescope and you are observing this object. So light will come and light will diffracted at this part. So diffraction occurs at the instrument, and that's why there you will see some diffraction pattern of that particular source. So if the diffraction pattern of a one source, that is seen by this line, this solid line, and that this I mean faint line is due to the other source, this is the two diffraction pattern of two different source. So if this diffraction pattern of the second one, suppose say for the lambda 2, if it is at the same position with the diffraction minimum of the first source. Okay, so I will write diffraction maxima of second source will be at the same position of diffraction minima. So you know, in the diffraction pattern there will be maxima minima of first source. Then that is the criteria of the resolution. So that much resolution you need to identify two separate objects. If your resolution is much better than this limiting value, that is very good, then you can see the two objects separately, but at least this criteria should be maintained, that diffraction pattern, that the maximum of diffraction pattern of one source is exactly at the similar position where the minimum of the diffraction pattern of the second source occurs. Okay, so that is the criteria, and if you calculate using that criteria, you will get that theta, which is the I mean resolving power, that should be 1.22 lambda by d. I will not derive it, but you just go through any standard diffraction chapter book where the diffraction chapter is there, and go through the diffraction pattern due to a circular hole. There you can get this resolution resolving power. So this lambda is the wavelength of the particular source and d is the aperture. Okay, aperture means the diameter of that particular. So in this case this was the telescope, and the diameter of the telescopic hole is actually the aperture. Okay, so if you now, so all the thing you have in your hand, just you have to calculate. So theta is 1.22 lambda by d. Okay, now for blue light, so for blue light the lambda lies between the range of 450 to 495 nanometer. I am taking a range because there is nothing like that particular lambda which is blue light, so it is a range. Okay, because if I show you, here you can see a spectrum. So roughly you can say this is the blue line spectrum from light blue to dark blue. So we are taking the range which start from 450 and ends at 495. Now if I calculate using this 1.22 into 450 nanometer means 10 to the power minus 9 meter, and your aperture has been given as 24 centimeter. Okay, so 24 centimeter means 10 to the power minus 2 meter, and it will give you 2.28 times 10 to the power minus 6 in radian if I use 450. And similarly, if I use that 495, then the value will be this. Just I am equating the range of the resolving power. So it will give you 2. So it is in meter, it is also in meter, 2.51 times 10 to the power 6 radian. Right. So if your resolving power is between these, that 2.28 into 10 to the power minus 6 radian to 2.51 into 10 to the power minus 6 radian, then you can critically resolve that source which is emitting a blue light. Okay, which is emitting a blue light. For red light you have to put that lambda which is corresponding to the red wavelength. So our answer is 2.28 to 2.51. Now you can see that so this 2.5 is the limiting case. So we will denote this. So because 2.3 is in between 2.28 and 2.51, so it is a safe option to mark that value which is in the range. 2.5 will be the extreme high value, so I will not mark that. So 2.3 is the correct answer according to me for this particular case. Okay, 2.3 times 10 to the power minus 6 radian. So this is the main thing. I will again emphasize this particular point, that Rayleigh criteria is very important for the calculation of resolving power, which just always try to remember this particular image where the peak of the first one, this thing, or the second, we will tell the peak of the second one, that faint line which is this peak is actually at the same position where the minimum of this source is coming. Okay, so the minimum is due to lambda 1 and the maximum is due to lambda 2 to different source. So that is the Rayleigh criteria, and that will lead you to this equation 1.22 lambda by t. Okay, just remember that. And here the theta, what you will get in radian. Sometimes you may have to convert it into degree, that is not a big deal. So just remember that. So if anyone have any question, they can ask. Problem. So this was the question from your assignment. Now a very easy question was there. I thought I will not put it, but whatever, I have put it in the slide. So this was given in your assignment, and there was certain region marked by these circles, and the questions are, there are 5 questions on this. That's what are the, range of these circles, what is the circles denoting, that type of question. So for comparison, I put the HR diagram which I found in the internet. So always remember that whenever you are seeing this type of plot, this is the main sequence. Okay, so this is this main sequence, and if you are at a y-axis at a particular x value, and if you are going upward and downward in the y-axis for that particular x value, that means particular temperature value, then you are going to a higher luminosity side. If you go upside, that means you are going to a higher luminosity side. If you go downside, then that means if you are going to a lower luminosity side, and luminosity is 4 pi r square sigma t to the power 4. Now it is, I am telling you to remember, I mean, you don't have to, you can do it by seeing the HR diagram. Always you don't have to remember that this is the supergiant, this is the white dwarf. If you don't know it, that is also fine. Just follow this, that if now I am at a particular x position, that means my t is fixed, so L value is r square. That means when we are going to a higher luminosity side, that means we are going to a higher radius, to a higher radius object, and higher radius objects means we are going to a supergiants. So these are the supergiants, and a little smaller than the supergiants are called the giants. So this is the giants as supergiant scheme where r is very large. Okay. Now similarly that can be done at particular this position also. Here at a particular so suppose it was the t1 value where I have fixed it. Now if it is t2 value where I have fixed the line, then according to the same equation, if you are going downside, that means you are going to a lower radius object, going towards a lower radius object because of the lower luminosity, because your t is constant on that line. That means you are going towards the lower radius object, that means white dwarf, because dwarf has lower smaller radius than the stars. So the main sequence is the stars population. So if r is greater than star, you are going towards the supergiant side. If r is less than the star, you are going toward the white dwarf star. Okay. Now all this is done. Now what is this and this? So this is actually the extension. I mean, this part is the extension of the main sequence. There are few stars, but actually those are very high mass stars, and the number of high mass stars is very less. That's why number of data points is very less, but this corresponds to the main sequence itself. Okay, and you can think of is at a blue star, and this as red star. Okay, so red, and accordingly this picture has the color coded. So this has been, the left side is so the left side has been coded with the blue to, I mean, give an idea about the blue star, what we nomenclature, the standard nomenclature to tell that blue star and red star. So if you are in this side, it is red star, and if you are in the, it is blue star and it is red star. Okay. You can see it from the figure. So now the question is why the higher temperature stars are blue and the lower temperature stars are red, because you know that in the HR diagram the T increases in this side, right? It is opposite to the standard thing. So this is 400, this is 30,000. So 30,000 temperature stars are blue and 400,000 temperature stars are red. Why is that? So we'll just give you some idea. I think you have already done it, but as my duty I will do it. So suppose you are going to the high temperature star. Okay. High temperature star means roughly I am taking at 3000 Kelvin. Okay. That's one value to calculate. Now according to Wien's displacement law, you know that I have told you in the black body radiation, that lambda mt is constant, and its value is, I have written down, 2.89 10 to the power minus m Kelvin. Okay. So this is the value. Now if you put your T of 30,000 Kelvin, you will get it as roughly, I am writing, just calculate it, 100 nanometer. Okay, so for a high temperature star we got the lambda as 100 nanometer, and similarly for low temperature star T is equals to suppose I am taking the temperature as 2000 Kelvin, the low temperature, that means 2.89 into 10 to the power minus 3 by 2000. So if you calculate, it will be around 700 nanometer. Okay, now focus on the spectra. This is the visible spectra. So 700 nanometer is correspond to this extreme point, that is the red point, because the wavelength, this is the wavelength of red. I mean, this is going towards the wavelength of red, and this 100 nanometer is actually beyond this limit. That means we can say roughly that this 100 nanometer is going towards blue color, towards blue wavelength. Okay, so that is the main point why we say that blue star and red star, because depending on the temperature you can calculate the lambda, and if your lambda lies in the range of red color, that's why we called it as red star, and if your lambda lies in the range of blue color, that's why we call this blue star. So that is the reason why the higher and higher temperatures stars we call as blue star. It is not that the star will look like blue itself, but it is going towards the blue wavelength, and the lower temperature stars are red star because it is going towards the red wavelength. It is a very easy thing, I mean simplest thing. I think you all have done it, but still I told you that this is why we called in the HR diagram the higher temperatures are blue and the lower temperatures are red. Okay, so I think you have understand it, and how the supergiant, giant and white dwarf are coming into the picture just depending on the luminosity. Just consider a particular x point, that means a particular y axis, and go above and below along that line. So eventually your radius will increase and decrease, and you will go to the supergiant giant side, or oppositely white dwarf side. I have told it in the first class also how to. If you forget, then also you can say that this is my red giant, this is my white dwarf, just by calculating the luminosity. I mean not calculating, just by looking at the luminosity expression. Okay, so I think it is done. Now I will go to another just numerical problem. I will not spend much time here. So find the luminosity of a star whose radius is given and surface temperature is given. So I have repeatedly told you that luminosity is 4 pi r star square sigma t to the power 4, where r star is the radius. So 4 pi, it is given 85 1 2 3 4 kilometer. So if I convert into centimeter, so 10 to the power 5 centimeter square. Sigma I am telling you repeatedly, just try to remember its value. Okay, 5.67 into 10 to the power minus 5 in arc second centimeter to the power minus. So try to remember the value of sigma in every unit. I mean in arc per sec, in CGS, in SI, in EV. So that is helpful. Just put it sigma here, and that temperature is given as 6000 Kelvin. So this is minus 4. Now if you do this calculation, I will not do, I have done it, 6.66 into 10 to the power 33 arc per second. So that is the luminosity of this particular star, which has a radius of 85,000 kilometer and surface temperature of 6000 Kelvin. So it is comparable to sun, because sun has this much radius and 5800 Kelvin, and for sun you will get roughly 3 times 10 to the power 33 arc per second. So it is a sun-like star which has a little higher radius, and that will give you 6.66 into 10 to the power 31 arc per second. This is important, and I think in exam also you will get at least one problem from this particular expression, luminosity, how it varies with radius and temperature. Now I think till now anyone has any problem or any other problems from your lectures of sir. So if you have any problem you can ask. If I know, then I will try to answer it today, but if I don't know, then I will try to tell you later. Okay, so here there is another question, nebula. It is also a theoretical question. It is a crab nebula. It is a very beautiful nebula. That's why I put the picture so that you feel some interest. So what are the correct for a nebula? Okay, so this I should not have written here. Okay, whatever. So which of the following are incorrect for a nebula? So they are smaller galaxies. So you know that nebula is a diffuse gas, actually diffuse cloud of gas you can say, and by the gravitational contraction, stars can be formed at that particular nebula. So at the center of that particular nebula, so there is no relation between nebula and galaxy. So nebula is not smaller galaxy, it is an entirely different thing. It is a diffuse cloud of gas. So each of them can be expanded up to hundreds of light years. That is right. So the radius can be, as it is a diffuse cloud, that the radius can be very high. Okay, they are made of H and He gas mostly, of course, so because all the astrophysical elements are mainly made of hydrogen and helium. It is acceptable. And they are solar nurseries. As I told you, solar nursery is not right word, but it should be written as stellar nurseries. Sun is a special kind of star. All stars are not sun, so they whatever they mean to say that stellar nursery, so it is acceptable. And they are as dense as Earth atmosphere, never, because the density of these clouds are very less, very less. That's why I am again using the word diffuse cloud. Diffuse means the density is very less, that's why the radius is very high. Okay, so you can think is that if you have a mass is like 4/3 pi r cube rho sigma. So if you have a particular value of mass, suppose this mass is constant for two different objects. Now that object which has a very high value of r, that should have a low value of density, so that m is constant, and in the vice versa, if your r is very low, then your density will be very high. Okay, and our nebula generally follows this. For this case, the radius is very high but the density is very low, and this is the situation for a white dwarf. So nebula and white dwarf are entirely on the opposite end of a seesaw, you can say. Okay, so this is very diffuse cloud, and they are remnant of supernova, right? Because the origin of a nebula is the explosion of the star. There was a star inside this Crab nebula which has gone through an explosion, and all the material which you can see right now, this all materials, this is actually the remnant of the star. That means the envelope of the stars has been blow off. So and that's why the remnant is there and the diffuse thing is there. So it is the origin. So as it is saying incorrect, so this and this will be your accepted answer. That they are smaller galaxy is entirely false, and they are as dense as Earth atmosphere, it is also false. So I cannot exactly remember the Earth atmosphere density. If I remember that, then I can compare it. So never whatever, so just remember that our Earth is much denser, our Earth atmosphere is much denser than the nebula. Okay, so a theoretical question it was. Now we are coming to a very good question. So existence of a star which is 15 times mass than the sun, that means we have to find the number means number of stars which has with mass greater than 15 solar mass. Okay. Now, if you just consider the okay, so here I have written it, just let me see. Yeah, okay, so it will be good to do it here. Now, as you know that it is the general understanding that the stars with higher and higher mass, the number falls down. That means you have a high number of stars which has lower mass, and you have a low number of stars which has higher mass. So obviously the answer would be that a rare case, because the number of stars which has 15 times solar mass, it is very less. Now I will give you small idea how we calculate it. Okay, so this is a Salpeter mass function, that is called the Salpeter mass function, which tells you the number of stars, how it varies with the mass of it stars. Okay, so it varies generally as, so this denotes the number of stars with a mass m, and here it varies as m to the power minus 2.35. It is called the Salpeter mass function. Okay, so in this plot here you can also saw it. This Salpeter thing is the blue thing. This blue line denotes the Salpeter mass function. So there are different types of mass function. That's why different plots are there. We will just focus only on the Salpeter mass function. So this has a slope of minus 2.35. Okay, this blue line. That means from this figure it is very clear that when you are going to a higher mass number, suppose this mass you are considering, the number is this much. So this is the number, and if you are a lower mass range, this is the lower mass range, then your number is very high. The number of stars is very high at the lower mass. Okay, now if we calculate it using the Salpeter mass function, that number of stars with mass m is going as m to the power minus 2.35, then using this definition of the initial mass function, we can calculate the number of stars within mass between m to m plus delta m. It is just a integration. So your n is n will be lambda, it is zeta, I think zeta m dm, where zeta m can be is expressed by this. Okay, so what is zeta m? Zeta m is actually dn by dm, which is proportional to zeta 0 m to the power minus 2.35. This tells you number of stars with mass m in the range of m to m plus delta m. Now from here, if you want to consider the number of stars, you just have to do a integration, right? This 2.35 dm. I have just put the dm here, and I am just integrating it in the range what you have given. Suppose it is given as m1 to m2. Now if you do this integration, you can get an idea about the number of stars with mass from m1 to m2. Now the result will be like this, the integration result. Okay, now a very interesting thing we will do, that we got our number of stars in the range m1 to m2 by this expression. Okay, now I will calculate the number of stars which have mass, suppose 0.0 m solar mass to 15 solar mass, and the number of stars which has mass between 15 solar mass and above, suppose 100 solar mass. So this is the thing which has been asked in the question, right? Existence of a star which is 15 times massive than the star. So I have divided into two range of mass. One is from 0.01 to, I am not taking the 0 because a small value is generally taken. So 0.01 to 15 solar mass, and 15 solar mass to 100 solar mass. we will see how this fraction varies. Okay, so this will be actually, if you just put this expression for the denominator and numerator, so zeta 0 and 1.35 will be cancelled out, and that will be just m1. So for the upper thing, the m1 is 0.01, or let me take it as 0.1 only, no problem. I need some non-zero value. Okay. So 0.1 minus 1.35 minus 15 minus 1.35. This is for the numerator, where my m1 was 0.1 solar mass and m2 was 15 solar mass. And for the denominator, it will be, the m1 is 15 solar mass, 15 minus 1.35 minus 100 minus 1.35. Okay, so I think you can understand that I have just written the number of stars between two energy range, which I have divided, and I have used this expression which is coming from the Salpeter. So just go through this particular thing. This is very easy to come to this result, the number of stars, just a simple trivial integration. Now if you calculate this particular expression, you will get the result as roughly 1000. Okay, so you can see that our number of stars between 0.1 to 15 solar mass and number of stars between 15 to 100 solar mass, it is very less than 1, because 1000 we can write it very less than 1. That means the numerator, which was number of stars in this range, is very greater than the number of stars which is in this range. Okay. So that means the number of stars which has lower mass is very greater than the number of stars which has higher mass. What I have just theoretically told you here, it can be calculated by a very small, very trivial initial mass function. So this initial mass function, that is called the Salpeter mass function, it is important to calculate it, and by doing this very small simple calculation, you can find that this is the result which is coming. And I will ask you to do the same thing. Just try to understand how many stars are there. So you can divide from 0 to 0.1 to suppose 8 solar mass, then divide it 8 to 15 solar mass, then 15 to 100 solar mass. So you can get a rough idea about the number of stars in this different solar mass, and you will see by going to a higher and higher side, your value will decrease. Okay, that means I should not give that sign here. So the number will decrease, it will be higher, then it will, what kind, if it is A, if it is B, if it is C, then your A will be B, will be C. It is the number that I tried to do it here. If you don't understand, please tell me, I will try to explain again. That is the main reason why the 15 times massive sun than the sun is rare, and lower mass stars are very common. Okay. Okay. So if I think there is no question, so I am telling again for all the students who are here, that in the chat box I have given that link. If you don't get it from the PMRF committee, I have told them also to give you the link, but if you want, you can also click, you can go to my playlist from here, there you will find all the previous videos. Okay, so this was another question. Now the number 10 question is very easy. I will just tell the answer. Our sun is a population 1 star, and you know that metallicity of population 1 star is higher, so it has a high metallicity, just that much. So if I am telling anything wrong, just tell me. Okay, sometimes I also made some mistakes. like in first class I have done some mistake, and in the second class I have told that was my mistake and I have corrected it. Okay. Okay, now coming to the nuclear part. So we are going now deep into the nuclear astrophysics, and this is a question about the cross section of proton collision. Okay, so first I will do the problem, and later I will, if time permits, I will try to give you an idea about the cross section, what actually the physical meaning of a cross section of a nuclear reaction. If I don't get time, then I will tell it in the next class, no problem. So you know that classically if we do the collision problems, then the cross section, I will not go into the quantum thing because here it will be calculated by classical method. So the cross section sigma, that is actually pi r of the target plus r of the, I mean here it is a proton collision, so my okay, so r of target and r of projectile. So in proton collision, you can think one proton as projectile and another proton is target. So actually it is the formula r target square plus r projectile square. That means in our case it will be for proton, whole square I missed, rp plus rp whole square. Okay, now you have given the r0. So what is the r0? We are talking about rp here, which is the radius of the protons, and in the question it is given r0. So what is the relation between r0 and rp? So that we want to establish here. So this will come from the relation of r, that is the radius of a nuclei, with a. That means a means the mass number. Okay, mass number. So that means this is a nucleus, here are z and n, so z plus n, that means proton plus neutrons are a, and the radius of this particular thing is r. So how the radius of this nucleus is related to the mass number a? Okay. So it is very trivial that a volume of the nucleus is proportional to mass number. Okay, that means if you have higher number of mass a, so suppose you have a 2a, instead of a you have 2a in this nucleus, and that 2a have to be accommodated in this particular nucleus. That's why the radius that will be bigger. So if it is a r1, this r2 will be bigger than r1, because now you have a large number of protons and neutrons, and the nucleus size will be bigger. Just think it as a tennis ball, I mean a ping pong ball and a cricket ball, or a cricket ball and a football. If you have higher number of air molecules, I mean particles, then the size will be bigger. So volume of a nucleus can be written down as 4.4 pi r cube, where is a, right? A is the mass number. Now that means your r will be a to the power 1/3. So your radius will be proportional to mass number to the power 1/3. Now here comes the r0. So if you try to convert a proportional relation to a perfect relation, that means instead of proportionality we want to use the equal to signs, then there will be a constant. Every time you do it in mathematics, that r is equals to r0 a to the power 1/3. This r0 is constant, and here it is called that radius to parameter constant. Radius to parameter constant. Okay. you can write nuclear radius to parameter constant, that is this r0, and this r0 value is given. Actually this r0 is that nuclear radius to parameter radius to mass number. I have not written the mass number. Radius to mass number parameter constant. Okay, so that is given. Now if so we will just put it in the sigma which we have calculated. So let me write it here. Sigma equals to pi, rp will be r0 a to the power 1/3. Similarly it will be also r0 a to the power 1/3 square. Then it is just trivial equation. You just have to remember the relation between r and a, and the constant is r0. And for a, you know that for proton a is 1, because there is only one particle, one nucleon in the nucleus. Okay, so that is a is 1, so that is pi r0 square, and r0 value it is given 1.3 10 to the power minus 3. You have, if you put it, then the value I have written it here. I have calculated it already. So this is 1, right? That's why I am not writing 1 to the power 1/3. No sense of writing that. So sigma is actually 2.1 times 10 to the power minus 25 centimeter square. Just put the r0 and multiply it with pi. Okay, so this is the thing. And if instead of proton, suppose there were helium 2He4 plus 2He4, and you have to calculate the cross section, classical cross section, then your a r0 is constant for all the values because it is a constant. So a will be 4 for helium. Okay, so a will be 4 for helium. So just replace that a which I have written here 1 for proton. Oh, sorry. So yes, no. So just replace that a by 4 to the power 1/3 plus 4 to the power 1/3 to the power square. That will give you the classical cross section of helium reaction. I mean helium plus helium reaction. Right? So generally that r0 value which is given, if it is not given here, it has given as 1.3 10 to the power minus 3, but it is very important to remember, because in many of the question you will find that the value is not given, and the examiner wants that the student should remember this value. So r0 have a range from 1.1 to 1.5 per fm. Fm is the I forgot the exact name. So it is actually I really forgot the name of FM, what was the name, but it is actually 10 to the power minus 15 meter. Okay, so fecometer or something, I forgot. Can anyone tell me the name? I don't know if anyone here or not. So 1.5 10, sorry. So that is 10 to the power minus 15. And if nothing is given, you can take that value of middle of this range, that is 1.3, which is given in the question. But remember the range, it is 1.1 femtometer, 1.1 to 1.5 femtometer. So this is the answer, and also what I got, 2.1 times 10 to the power minus 25. So this is the answer, this one. Now I think it is done. Okay, now coming to this problem, this is also taken from one of your assignments. That today I didn't get time to arrange those problems, so it may be random, but all the problems are from assignments. Just go to your assignment and find out which problem where I have done it. Okay. So more massive star will not, what will be the answer? Will not. So I have told you that repeatedly the lifetime of a star depends on the mass by luminosity. That I have also done in the last class. You can see that T varies m by L. Now at first, at the beginning, I told you that we have done some interesting thing. Where, just a second, here. So here you can see that ML relation. that is needed because I want to write the luminosity in terms of m. So if I write it here, L will be m to the power 3.5, which will give you m to the power minus 2.5 roughly. That means if your mass is increasing, your lifetime is decreasing, because it is proportional to 1 by m to the power 25. It is oppositely related. That means more massive star will consume available nuclear fuel more rapidly, right? Have a higher energy projection, also right, and have a larger lifetime. It is wrong. So it will have a lower lifetime. So the correct thing would be lower. I mean not larger, shorter, not lower. It is shorter lifetime. So this will be your correct answer, because it has asked which will not follow. So this you can also find in the first or the second, in both tutorial I have done it. Okay. So I will not go into the much details of it. Now binding energy per nucleon, this is something I will do. Let me check. Yeah, this I have done already. Okay. So binding energy. So you know that what is a nuclear binding energy, because when you calculate the mass of a nucleus and the mass of the constituent of the nucleus, that is proton and neutron, there is some difference between those two. So suppose this is a nucleus which has been created by combining Z proton and N neutron, and the mass of the nucleus is m NuC. So there is a difference between the constituent mass, that means the constituent particle mass, that is Z times mass of proton, mp is the mass of proton, plus N mass of neutrons, because this has been come together to form that nucleus, minus the mass of the nucleus. Okay, so there will always be a difference between the mass, which is called the mass defect, and the binding energy is actually the mass defect times c square. This is the binding energy of the nucleus. That means this is the energy which is required to keep all those nucleons inside the nucleus. You can think of like that. That is called the nuclear binding energy. So that's why I have taken it from the internet. The nuclear binding energy is the energy required to separate. You can think it as separation also, that the nucleus is there. Now I want to separate all the protons and neutrons from that combination of in the nucleus. So you have to supply some energy. So that is called the nuclear binding energy, which helps to bind the nucleus and protons. So to separate an atomic nuclei completely into its constituent protons and neutrons, or equivalently the energy that would be liberated by combining individual protons and neutrons into a single nucleus. So that is called the nuclear binding energy. Okay, so this is the EB equals to delta m c square. Now for helium we can calculate it very easily, that for helium it is, there is 2 protons 2 neutrons minus mass of 4 Ag times c square. Okay, now if you put all this mass which is given in AMU unit, and 1 AMU unit will liberate energy of 931.5 electron volt that we will use. So the delta m, that will be 2 into 1.00727 647 plus 2 times the given value, I am just putting it here, minus 4.00260324. You can see the precision of measurement. It is 1 2 3 4 5 6 7 8 9 decimal point up to. Okay, so times 931.5 mega electron volt as 1 AMU gives this much energy, and if you calculate you will get 0.02927996 times 931.5 mega electron volt, which will give you 27.70 MeV. Have I done anything wrong? Okay, so this is the total binding energy. Okay, that is mistake generally students also make. So this is the total binding energy. Now if you want to calculate the binding energy per nucleon, so please focus on the point. I mean, what is the question? Is it the total binding energy or is it binding energy per nucleon? So binding energy per nucleons means EB by A, number of nucleons, and for this it is 4 because 2 protons and 2 neutrons, and if you divide it by 4 it will be 6.8185 MeV or roughly 6.82 MeV. Okay. So the correct answer will be 6.82 MeV. It is the binding energy per nucleon, which is I mean more generally used in calculations or in everyday physics. So that's why I have put a figure of the binding energy per nucleon. So yeah, so here this is the binding energy per nucleon plot, and you can see that it starts from hydrogen and the peak is at iron Fe. So here the peak, the binding energy per nucleon is maximum. That's why this is the most stable element, and there is some peak. You can see these peaks. So all these peaks are at particular numbers. So like the peak is at helium. So at helium there is a peak, at carbon, at oxygen. So there are peaks for these elements in the binding energy term. That means peaks means those elements are more stable than the others. And if you compare, I mean the abundance, solar abundance, that means the abundance in our solar system, that is there you can also find that there is some peak in helium, carbon, oxygen. So you can I mean, can you relate that the peak in the binding energy at which elements the peaks are, same peak is here also, Ag, carbon, oxygen. So that means that binding energy is playing some important role in the cosmic abundances also. If a element is formed in the space or in the solar system which has a higher binding energy, that will be stable. So the abundance of that particular element will also be higher. Okay. So EB by A is higher for those elements Ag, Co. Similarly, as a result, the abundance of HeCO is also higher in solar system. Okay, so that you can compare the peak of the binding energy with the peak in the solar abundances, I put those two plots side by side, and you from this you can also have an idea that yes, the binding energy is playing some important role to determining the solar abundances. Okay. So if there is any question till now, you can ask. I will just go through my notes if I am missing something. Okay, this is done. This is also done. Okay. Now one thing I found that I have to go through that cell model and that liquid dwarf model, but I have not taken any question from that for this class. That I will do it in the next class. Briefly, if possible, I will tell you the how to calculate the spin parity from the cell model and what is the drawbacks of a liquid dwarf model if I get time in the next class. Okay, so that's I just told you. Okay, so we have done this question that binding energy per nuclear for 4He. I have calculated and I have compared those two plots also. Now coming to some more deep nuclear reactions or nuclear astrophysics. So here the question is, these are the two questions from two different assignments, and both questions are more or less similar. Okay, so that's why I have taken the two question here. And so here you have to calculate the mass fraction of 1H1 and 4Ag in the solar interior. Oh, so the mass fraction is given 0.73 and 0.25. The mass fraction is given. That means if you have 100 mass, 100 okay solar mass, if you have a 100 solar mass object, 73 solar mass is into the hydrogen and 25 solar mass is into the helium. 73 plus 25, that is 98. That means 2 solar mass is in another element, so mainly hydrogen and helium. Now these are the mass abundance, mass, and from here you have to calculate the number density. So that we will do. I will just tell it very easier way. So suppose this is a mass m. Okay, so this is a mass m of any object. Okay, and suppose it is made of particles, one type of particles only for now. Suppose that made of particles with mass number a. Only one type of particles are there. I mean, here there are small particles made of one type of particles which has mass number a, and that means these particles which has mass number a, they have mass of amp, right? Because a means the number of protons in the nuclei and mp is the mass of the protons. That amp is the total mass of that particle. Okay, now so if you have, suppose, total n number of particles inside this mass and each particle has mass of amp, that is proportional to total mass, because here I have considered that whole mass capital M is made of a single type of particles with mass number a. This n is the total number. Now so this n, that is the total number, is the total mass by mass of each particle. Now if you want to convert it into the number density, then you have to just divide it by the volume of that particular thing. So this is the most easier expression. Oh, so this is small n, small n. So actually small is n is equal to capital N. Capital N is the total number by the total volume, that is the total number density. So if your volume is constant, that means your n will be proportional to m by a. Okay. Number density for a constant volume, suppose there are two mass of constant volume, so there that will depend at n varies m by a. So this is the thing. Now from here we will calculate the here it is given the mass fraction is given in the solar interior. That means we are considering the volume as the solar sun, so the volume is constant for this thing. So that's why I write it as E, because if it is only true when V is constant. Now for our problem, V is constant because it is inside the sun, solar interior. So from this easy thing, that you can write number of 1H1 by number of 4, number density, not number, I should not tell it a number, is actually mass of 1H by mass of 4He times A of 4He by A of 1H. I have just written from this equation, okay, that number density of hydrogen with number density of helium. And in your question it is given the mass fraction is 0.73. Mass fraction is 0.73 means, I mean, how can I say it? Mass fraction means that how much mass of the total mass is in that particular nucleus. So 0.73 of the total mass, suppose say this is the mass of the sun, it in the hydrogen, and 0.25 of the total mass is in the helium, and A of Ag4 is equals to 4 and for hydrogen is 1. So that solar mass will be cancelled out and it will give you the answer as 11.7 by 11 1. That means 12 by 1. So the ratio is actually number density of hydrogen is to number density of helium is 12:1. So that can be calculated by using this very easy mathematical expression. You don't have to bring that density or the Avogadro number in this calculation when you are inside a same interior. That means the volume of the interior is same. So that is 12:1. This is the answer. Now the same thing, the same type of question I have taken it from another assignment, where instead of hydrogen and helium it is given in terms of carbon and oxygen, and you have been asked to calculate what is the number density ratio of carbon and oxygen. So similarly, just I will put the values 12C by 16O is actually, here it is given 0.33 for carbon and 0.45 for oxygen, times mass number of oxygen, that is 16, and mass number of carbon, that is 12, which will give you 0.977 or 0.98. So this is the ratio of number density of 12 carbon and the number density of 16 oxygen, 0.98. It is the answer. So the same question, same type of questions, as the values are different, just these values are different from the previous value, but it is very easier way to calculate, just by considering a mass made of some particles with some mass number, and from there you can easily calculate the total mass of the particles is total mass of the object which is given here. Okay, so I think you can calculate it for any other elements if those are given. Now this I will not do into details, that for supernova events, so again I told you that the old assignment and the new assignments are more or less similar, just they have changed some values, they have put some question instead of first assignment in the second assignment, all those permutation and combination. So in there it was given that for a supernova events where T is 500 degree, calculate the most probable energy of the particles, and you know that most probable energy is just the kBT. So your kB is I have written down the value, so remember those values last. Okay, so it is 8.617 into 10 to the power minus 5 eV by Kelvin times 5000 Kelvin, and that will give you 431 keV, just equals to kBT type of question. We have done it several times. Here also the T is just difference, so instead of 5000 here it is given is, oh, here T6 is 300 given. So remember T6 the type of, oh, I have also did not focus it here. Okay, so Tn, whenever you face this type of term, it is actually T by 10 to the power n, that is expressed by Tn. So that means T6 is T by 10 to the power 6. It is given as 5000. That means your T is actually 5000 times 10 to the power 6 Kelvin. So this is a standard nomenclature of astrophysics. We express like this, like sometimes we express M4. That means what is the mass times 10 to the power 4 is actually the value. So this type of expression is very useful for astrophysical scenario. So this will not be 5000, it will be 10 to the power 6 k. I have done correctly in my rough sheet, so I have put the correct thing and here. So the t value will be 300 times 10 to the power 6 k. Just put the t with kbt and you will get your answer. I have not done that answer, just find it what will be the value. So just kbt, put kb and t and you will get the answer. Okay, now it is a theoretical question that half life, not theoretical, you can calculate it also, but I have not calculated that particular thing. So half life of a free neutron is, it is roughly 10 minute we say. So this 611 second is roughly 10 minutes. That is the answer. It is a well known fact, so I will not go into the theoretical calculation of this. The half life of a neutron is 10 minutes roughly, just remember that. Okay. Yeah, now this is the important thing for the third week course mainly. For the stellar temperature T9, so again you see T by 10 to the power 9 is 0.01, that means your T is 10 to the power 7 k, right? Yes. So this is the temperature is given, the energy is given. Okay, so the energy value of two state has given it to the E equals to 550 and E equals to 0.86. Now we have to calculate the number of particles. It is a very good question, so I will tell how to do it. Okay. Okay. So for this we need to remember the distribution function, the probability distribution function, which has been done for Maxwell-Boltzmann distribution for this type of distribution. So the probability of V with V, so it will, I will say it as n number of particles with V. So this is a Maxwell-Boltzmann distribution, and the probability of finding a particle, this P means probability in the energy range dV. So let me write it here. PV dV is actually m by 2 pi kt over to the power 3 by 2 exponential minus mv square by kt 4 pi v square dV. Okay, so it will be I think mv square by 2 kt. Just a second, let me check it. Boltzmann distribution. Yeah, it will be 2. I just forgot. So mv square by 2 kt. So it is the probability of getting a particle in the velocity range v to v plus dv. Now if we convert it as E, because always we can convert it at PE, so PE dE, because our E is actually half mv square, where is the kinetic energy of a particle. So that can be written as m by 2 pi kt to the power 3 by 2 exponential mv square by 2 will be replaced by E by kt, and okay, so okay, so I don't need this for this exact calculation. This I will need in the in another question. So just I will write that from PV dV the phi v. Okay, so phi v is actually 2 pi kt 3 by 2 exponential minus m v square by kt times v square proportional to, because I have not written that 4 pi term or anything, and I have eliminated the dv from the both side. So phi v is tells you that probability to find a particle, I will write this line because it is important, with the velocity between v and v plus dv. Okay, So this tells me how many numbers of particles are there with a velocity between v to v plus dv, and if I convert it into energy, it will be m by 2 pi kt, that term will be constant, and exponential 3 by 2 exponential e by kt, and you know that v square is proportional to e, so e is there. So actually v square will be proportional to 2e by m. I have not written everything, so you can see 2 by m term will be also there, and there will be also other terms. That's why I have used that proportional term, not equals to term. Okay, that my main motto is that my phi e is proportional to e times exponential minus e by kt, which tells you the number of particles with energy range E and E plus delta E is this much. Okay, so this is the probability distribution of particles with having energy E and E plus dE. Now it has been asked that my E, I have been given with the energy value up to state, you can say, and we have to now find the number of particles. So the number of particles will be proportional to this phi e, because it is the distribution function, and distribution function itself tells you what will be the number of the particles. So the number of particles will be just proportional to that, and I will write it as like this. So phi at E 550 keV, which is given by phi of 0.86 keV. So these values I have taken from here, and that will be E, which is for this 550 keV exponential minus E, again 550, okay, divided by kt. So kt, I will not write the value of k, I have in the previous question. Okay, let me write it, 8.6 into 10 to the power minus 8 in keV, k inverse times 10 to the power 7k, right? This 10 to the power 7k I have calculated here. T9 is 0.01, that means t equals to 10 to the power 7k. This divided by, so I think this question you have not faced till in your assignment, but this type of question will come surely. keV exponential minus 0.86 keV divided by again k inverse 10 to the power 7k, right? So e to the power a, I write it as exponential a, just don't confuse it. Exponential a means e to the power something. So I think you have also see this type of expressing of exponential. Okay, so if you calculate this and all the values are given, that there is no variable or anything, so that just put it in any of your computer language, or I have done it by using Python, because this is the exponential term is very weird looking. You can do it in your calculator also. So the value will be 3.12 10 to the power minus 275. This value I got. So the number of particles at 550 keV by number of particles at 0.86 keV is equals to 3.12 10 to the power minus 275. That means it is very less than 1. So the number of particles at a higher energy, which is 550 keV, the probability of the probability of staying at that energy level is much more less than probability of staying at a lower energy level. So in the vice versa scenario, we can think of the number of particles in a lower energy level is higher than the number of particles in the higher energy level. Okay, so 3.12 times 10 to the power minus 275. So the power is mainly important for this question. So this is your answer. This type of question you will also face if you have not faced it till now. So just calculate it how I have done it. Okay. So here the distribution, you have to remember the distribution function, how the Maxwell-Boltzmann distribution will look like, because that will give you the number of particles at a particular temperature, because this curve is at a particular temperature. particular t. If the t is different, by this expression or this term, your probability, or also this term here also there is a t, the probability will be different, but the shape will be same, the number will be different. Okay, so this was the question. Now coming to this question, that in a, so till now any question? Okay, if not, then I will do it. I don't have many questions. So this here in stellar plasma. Oh, so it is a theoretical question. Sir have already done it in his calculations. So you can see that. I will just a second. Yeah. So okay, let me tell you very briefly. This 10, this 11, this 12. 3 questions are there only. It will not take much time. Okay. So this question and this question, that means 10, 11, 10, this 3 and this 9, all these are related. That's why I put it in at the last, because for it you need some theoretical background. Okay, so n is equals to, just a second. This is done. Okay. Just give me some time. Yeah, so that problem which I have done in a different way, this one, this number density, that you can also calculate using that expression which is there in the lecture, that Ni is actually rho Na xi divided by mi. Using this you can also calculate that, like for hydrogen it will be rho Na x of hydrogen and m of hydrogen. So m of hydrogen, you know, x of hydrogen is given here, that is 0.73. you know the Avogadro number, and if you divide it by n of He, then this rho will be cancelled out, so there will be no role of rho. So by using this expression you can also calculate the number density of hydrogen by number density of helium, which I have done in a separate way, which is easier, I think, according to me, but this is also absolutely fine to do it with this. Okay, so just matter density, just remember this thing, this matter density is rho Na xi by m. I will not prove that thing because it is done in SAS class. Now one thing, in the mean life we will do that problem. Okay, this problem I will do first, that mean lifetime of combustion of 2 protons into deuterium in the sun is how much billion years, how many billion years, with that we have to calculate, and it is given that your sigma v is this much, stellar density is also given, and hydrogen mass function is also given. So all these values are given. Now we will calculate the mean lifetime. Okay, so mean lifetime is expressed by nh sigma v. I will not go to the proof of this particular thing because it will take many time, long duration, and you can find this proof in the class itself. So I will not do it. I will just write it. So that will be rho x2 divided by Na sigma v, that is there, and 1.0078 is it given? and this MP. I think all of you have gone through the lectures and you can relate what I am writing here. So in the third week lecture it is given there itself. Okay, so now I find another question of the same type, but they are this all these values that Na sigma b, all those are not given and you have to calculate those values by hand. This question was in the older assignment, and for that you have to do a lot of calculation, and they have also suggested some books which you have to go through to do that problem. But this problem I have taken from your recent assignment. Here you don't need any type of that because all the values are given itself. Okay, so we will just calculate. You will just see that by putting those values I will get the result. So the rho is given as 100 gram per centimeter cube. Okay, this Na, okay, this NaV, all this value is given. Na sigma v, you can see the total value of Na sigma v is given, which is 7.9 10 to the power minus 20 semi cube mole inverse second inverse, and divided by mass of protons 1.0078 in AMU. So I will convert it into my CGS unit. 1 AMU is 1.67 into 10 to the power minus 24 gram, and as I have multiplied a Na here, we have to divide it by that because the value which is given in terms of Na sigma v. So you have to divide it because otherwise you will get the answer in mole. So you have 6.023 into 10 to the power 23 number of atoms in 1 mole. That's why I have written it as mole inverse, that means by mole. So this mole inverse and this mole inverse will be cancelled out, otherwise you will get the answer in mole. Then you can also divide it by the Avogadro number, no problem. So the thing is you have to get rid of that mole, and this semi cube is gram by semi cube, that means semi cube is in the denominator, so this will cancel out this thing, and this gram will be cancelled out. So you can see here you are left with the second inverse, and outside there is also an inverse. So second inverse that will make it a second, and we are getting a unit of time which we need. Okay, so it is 100 times 7.9 10 to the power minus 20 into so one thing I have missed, that XH2. So XH2 I have not put, which is given 0.5. I have missed that completely. So 0.5 divided by this 1.0078 1.67 10 to the power minus 24 6.023 times 10 to the power 23, and the unit is second now. Okay, so that will give you 2.55 into 10 to the power 7 second. Now a very useful formula to remember how many seconds are there is a year, that is pi into 10 to the power 7 second. So just remember, it is nearly that, it is actually 3.15 times 10 to the power 7, but it is easier to remember if we consider that as pi. So pi times 10 to the power 7 second is there in a single year. So if we divide it by that, this will be 17. What a blunder. Yeah. So pi into 10 to the power 7, if I divide it, so second will be cancelled and the unit will be year, right? So that will give you 8.09 into 10 to the power 9 year, and 10 to the power 9 year means 1 billion year, that means 8.09 billion year. Okay, so this is your answer of this question. So you can see that it is only a value putting type question as this. You don't need any complex calculation or anything, just every values are actually given. So if the value of Na sigma v was not given, then it will be a much harder to do it, but it is given fortunately. Now that is 8.09 billion year for this problem. Okay. I will do that problem also in later class, when the Na sigma v will not be given and you have to calculate it from the basic theory. That I will do also, but for this class I think it is the easier way. Okay, so mean lifetime we have calculated. Now coming to this problem, this is the I mean class, this problem has done in class, but I will just write it. Is it? Yes. So okay, so one thing, and that you can see, in a stellar plasma the nucleus 25 Al, it can be gone through the proton capture and it will create the 26 Si nucleus silicon, and another process is 25 Al will go to beta decay. I am not writing the total equation. So this is the 2 channel, and the question has been asked that which one is the first, I mean the dominant process. Which one is the dominant process? That has been asked at a particular temperature. T is 0.3 GK, that means 0.3 gigakelvin, means 10 to the power 9 Kelvin. Okay. So at this temperature we have to determine what is the I mean dominant mechanism, dominant equation reaction, I can say. So that mean life which I have calculated in the previous thing, just try to remember this expression, okay, because every time you cannot derive it from the basic theory, it will take a lot of time. So just remember some of the equations so that you can do it quickly in your exam. So that's the same thing we will also use here, that tau of, that is the mean lifetime of proton capture, that's why I am writing at P 25 aluminum is actually rho xp by mp Na sigma p, the same thing which I did it in the earlier scenario. But in this question I will point out one particular thing that is important. So here everything is given also, rho 10 to, it is 10 to the power 4, okay, not 104. So 10 to the power 4 gram per semi cube, it is a printing mistake I think, and the mp is 1.67 10 to the power minus 24 gram. Rho mp I have put xp, so xp is given 0.7, xp or xh, hydrogen or proton, same thing, 0.7. Na sigma v, Na sigma v is also given, it is 1.8 into 10 to the power minus 3 semi cube mole inverse second inverse, and if you do it you will get the answer in mole. Just to convert it, divide it by the Avogadro number. Exactly similar step I am following as I did in the previous question. So the final result will be this semi cube, gram. Oh, this is the mole inverse unit, and 10 to the power 4 times 0.7 divided by 1.67 10 to the power minus 24 times. I am just rewriting that in a fresh line to take that second out of the inverse. Oh, that inverse I missed. Have I missed it here also? Yes. So that inverse will be there. Yes. So that will give you 0.079 second or 0.087. So the proton capture has a lifetime of 0.08 second, and now the another channel which was the beta decay. Now for the beta decay we will calculate the tau for the beta decay, and as it is going through that beta decay channel, it will be like the radiative decay. Beta decay is radiative decay, that's why T half. So you know that half lifetime everything comes when we are considering a radiative process, radiative decay process. So T half is given, T half is 7.18 second half life of beta decay. So this is 7.18 divided by 0.693. So if you calculate it, it will be 10.4 second. So you can see that mean life of the proton capture is much more less than the mean life of the beta decay. That means which reaction have a lesser time to occur, that will be dominant. It is like you want to go from a point A to B. You have two roads, one takes you 8 minutes, one takes you 1 hour. You will choose that 8-minute step. So that is the same. This is the same analogy, that which reaction have a smaller lifetime, that will occur very rapidly, and that will dominate the total process. So actually this proton capture will dominant process than that tau, beta plus decay. The the sole reason, that is tau of 15 AL is much smaller tau of beta plus decay. Okay, so which reaction has a smaller time, that reaction will be dominant over the other. This is the thing. This has been done in the class, just has been taken from there. Okay, so this was the 10th question. And one thing I want to mention, so you can ask what is the use of this 0.3 gigakelvin here. I have not used that value in the whole calculation, right? But the point is that yes, okay, so the point is that when I am putting this sigma v, Na sigma v or the sigma v, whatever, so I am focusing that this particular term. So sigma v is actually given by sigma, which is a function of v, p, v, v, dv, right? And in terms of energy, sigma e, p, e, d, p, v, d, v is root over e. We will convert it later. I am just following such step. The main point is that p is the probability distribution function of the Maxwell-Boltzmann thing, and if you write it in a correct way, it will be 8 by pi m half 1 by kt 3 by 2 0 to infinity e sigma e to the power minus e by kt d. So the main point of writing this equation is actually here the T was given as 0.3 gigakelvin. So at this particular value of temperature, you have to calculate the sigma v, because this sigma v is a function of T. Okay, function of T, because here the T is coming. So whenever you are given some value of sigma v, suppose this sigma v value is given in your question, so it is, you have to, I mean it is a rule, not a rule, it is always required to say at what temperature that sigma v is given. Okay, if your T is not 0.3 gk, suppose it is some million Kelvin, then your sigma v will be different from the sigma v you have used in this particular problem. So here that sigma v which is given, Na sigma v or sigma v, it is a function of temperature, and at this particular temperature the value is this 1.8 10 to the power minus 3. If temperature is different, then this Na sigma v will be different. That's why this is given that at this temperature the sigma v is this, because if you have not given this sigma v, we have to calculate it by the first principle using the temperature. So apparently you can say that there is no use of T equals to 0.3 gk, but the information of that temperature is already built in this particular value. Now this, for this question it is given, so that it is for easier, we don't have to look for any value of T, but that point I wanted to make, that this T is implicitly in the value of Na sigma v, which is hidden there. Okay, so this was the point, that's why I took this problem. When I was doing the problem, I also was confused why this T is given here, there is no need of that, but that is implicitly has been accounted for. Okay, so that was the question. So what is the answer? That proton capture will be dominant. Right? Proton capture. Now coming to the last question. So two things I could not do it today, that is the liquid drop and cell model. I will try to cover it in the next video, I mean next tutorial. And another thing, just a second. Okay, so the physical significance of the reaction cross section, I mean what is that physically means. So okay, that I will do in the next class, no problem. That will take just 15 to 20 minutes at max, no problem. Today there were many problems because I have covered the all previous three assignments also. So here it is given that it is a theoretical question. Consider the reaction 25 Al aluminum to silicon at temperature of 10 GK. Net energy production in a state due to this reaction. So okay, so net energy production, that will depend on forward reaction as well as backward reaction. Okay, that means when aluminum is converting to silicon as well as when silicon is converting into aluminum, all the both of this equation, both of this nuclear reaction will contribute in the energy production, because if suppose here delta E energy is produced and here delta E energy is absorbed, then the net energy will be 0, but in stellar atmosphere the rate of reaction of forward and reverse is not same. That's why we get a delta, resultant value of energy. So but the point is that all the forward reaction as well as the backward reaction both will contribute in the energy production, and I think this will also contribute because it is coming from the forward reaction, it is coming from the backward reaction, and Q value is also important. So okay, so the put a question mark here. These two I am sure that, and I have to find out how they are how they meant this Q value, because Q value is also important. Ideally all of them will be the ideal answer, but I will again go through this question whether how they are considering the Q value, because this Q value is actually inbuilt in the reaction rate. So for the time being, just consider that all of them will be the correct answer. I may be wrong also, I am telling you. I will just re-verify it, what will be the total answer. These two I am sure. And the Q value is also important for a reaction. That will tell you whether it is a absorption, the energy will be absorbed or energy will be released. So according to me all the three is important, but still I will look again into this question. Okay, so this was the thing which I wanted to discuss today. The two theoretical part I could not do it. I told you I will do it in the next class. So if you have any question you can ask me, and just I will ask any one of you, just please send me the assignment number 4, okay, which you have got, because which assignment I have, that is the older version. Just send me the new assignment into my email address, like one of the students sent me in the last week the 3 assignment. So oh no, sorry, so just send me your new 4th assignment in this email ID. I will go through both the old assignment number 4 and the new assignment number 4, and I will try to put the problems which are important for this course, and I will try to solve this. Okay, just please send me in this email ID your 4th assignment. I don't have the access of the new assignment, that is the main problem. Okay, so if you have any question now you can ask from anywhere up to 3rd week, because I have not also gone through the 4th week materials, so I will try to answer it. Okay, so today our main focus was that rate of reaction or reaction rate, mean lifetime of reaction, that number density. This things are the new what we learned, or we solved some problems related to these topics from the third week. And also uh, reaction rate, mean lifetime, number density, that probability distributions, number of particles, all this. So these are the new topic from which we have done some of the problems. Okay, so if there is no question, then I think we can end it today, and we will meet again next week the same time from 6 p.m. So okay, then thank you very much. I will end the meeting here.